Hi guys, welcome to Learn Electronics Repair. Today we're going to talk about PWM, or pulse width modulation. This is a very common technique or circuit found in electronic devices. In modern devices you find this in just about everything. Okay, so what is PWM? Well, pulse and width are fairly obvious words. What they mean, it's the width of a pulse, okay? Modulation. This is where some signal is transmitted on a carrier. That didn't tell you a lot, did it? Let me show you and this will become clear. So, let's imagine a circuit with a light bulb and a switch, okay? So we have a switch, and we have a light bulb, an old-fashioned incandescent light bulb, plus and minus, okay? When we apply a voltage and we close the switch, we know this, the current flows, conventional current, plus or minus, through the light bulb, and the light bulb will light up. If we apply sufficient voltage to match the rated voltage of the bulb, it will light up to full brightness. Okay, now what happens if we want to make our light bulb light up at half brightness? Well, what we could do is we could take the same circuit, again we'll have our switch and then a resistor and our light bulb. Looks like a bit of broccoli, I know. Okay, circuit. And when we close the switch now, the current passes via the resistor. And we know that a resistor resists the flow of current. So the voltage appearing across the light bulb will be a proportion of the supplied voltage. Let's say this is 12 volts and this is a 12 volt bulb, okay? If we fit a resistor that has the same resistance as the light bulb, half the voltage will now be across the resistor and the other half will be across the light bulb. So the light bulb basically now has 6 volts here, this is 0 volts, and it will light up at half brightness. Fair enough. But what about the wattage? Let's say our light bulb is one of these really bright headlight bulbs, okay, something like, I don't know, 72 watts, okay. When we had this original circuit, the full voltage was on the bulb, and this bulb was shining, and it was radiating effectively between heat and light, 72 watts of energy. What happens now? Well, the light bulb has half the voltage across it, so it's now glowing dimmer, okay? And without going to the efficiency of the bulb, it's now radiating half the power, 36 watts. What about our resistor? Well, that also has 6 volts across it. 12 minus 6 is 6, so there's 6 volts across our resistor, okay? 12 volts this end, 6 volts this end. And what current is flowing? The same current that's flowing through the light bulb. It's all a loop. The same current flows everywhere. So what wattage or in heat is our resistor dissipating? Okay, well, it's dissipating 36 watts. So the total power being dissipated by our circuit is still the same, 36 by the resistor and 36 by the light bulb. The resistor won't glow like the bulb does, it will get hot, unless you fit a resistor that can't handle the 36 watts. And then our resistor will glow, also, it will tend to burn out too, so it won't glow for very long. But at best case, and with a suitably powered resistor, suitably power capable resistor, the efficiency of this circuit is 50%. Yeah, at best, when we're on half brightness. Actually, I make a beginner's mistake here. I'll show you this. I'll leave it in because I want to show you how easy it is to fall into these areas, especially if it's a Friday. Okay, so just back to Ohm's law. If we take our original circuit with our broccoli light bulb, okay, 12 volts, and it's a 72 watt bulb, we can easily work out the resistance of the light bulb. But we need to do that anyway to put the same value resistor in, as I was just mentioning. So the way we do that is we first need to know the current flowing through the light bulb, and that's easy because watts equals volts times current. We know the volts is 12, so current equals watts divided by volts. Okay, and we know that is 72, and we know that is 12, so we know it is 6 amps. So that is the current. What's the resistance of the bulb? Well, this is easy as well. Ohm's law, V, I, R. Okay. If we want to know the resistance of the bulb, ignoring the fact the resistance will change with temperature, okay, but if we want to know the resistance of the bulb when it's lit up, we simply cover over the thing we want to know, R, and that's the formula, V over I. So R equals V over I, and we know what V is, it's 12, and we know what I is, it's 6 amps. So the resistance of the bulb is 2 ohms. Okay, that's basic Ohm's law. Now, if we want to make this glow at half brightness, I say half because it won't be exactly because the temperature of the filament will change, etc. But we put our resistor in here, our light bulb, 0 volts. The resistance of the light bulb is 2 ohms, so we put a resistor here which is 2 ohms. We now have, as I described before, half the voltage across the light bulb and half across the resistor, so the voltage here is 6 volts. What's the current? Well, we know what current is, it's V over R. Okay, just cover up the I and we need V over R. So the voltage applied to the circuit is 12 volts. And the resistance, well, it's now 2 ohms plus 2 ohms because we've added a resistor. 2 plus 2 is 4. So 12 volts over 4 ohms equals 3 amps. Makes sense if you think about it. We've doubled the resistance, we now have half the current. So what's the wattage dissipated by our light bulb and by our resistor? Well, it's not 36 watts each. Again, we know what watts is. Watts equals V times I. Okay, the voltage across the bulb is now 6 volts, half the voltage. So for the bulb is 6 times the current, we know is now 3 amps. 3 equals 18 watts. And the wattage dissipated by the resistor is exactly the same because it's also at 6 volts across and it's also passing 3 amps. So that's the actual wattage. The resistor will still glow if we put a small enough one in there. And the efficiency of the circuit is still at best like 50%. Okay, so that's the sort of mistake you can make. Hands up, I could edit this stuff, but no, I'll show you sometimes even I get it wrong off the top of my head. Now you know how to work that out, so you've all learned something more, hopefully. Let's continue. So how do we get around this problem? Well, we need a method by which we can provide the lower voltage to this bulb, 6 volts, to make it glow dimly, which we want to do, half brightness. But we don't want to waste the additional energy. And we can actually do that quite simply. So if we go back to our original circuit, this one, okay. And let's have a look what's happening to the voltage here on the top of our light bulb. We put our multimeter across from here to here. Yeah, let's make it a bit obvious. This is getting messy already. From there to there, okay. Well, the circuit has two states. It has the state in which the switch is closed and the state in which the switch is open. When the switch is closed, and this is a 12 volt supply, we will have 12 volts here. Okay, when the switch is open, we'll have 12 volts here and we'll have 0 volts here because the switch is open, 0 volts. So we can switch the supply to the bulb between 12 and 0. But look what's happening in the condition of efficiency. When the switch is closed, this is effectively a short circuit. So all the 12 volts appears across the bulb and none of it appears across the switch. The wattage dissipated by the switch is the voltage dropped across it times the current. So we can see if this again was a 12 volt 72 watt bulb, we actually have 6 amps flowing. The voltage across the bulb is 12 times 6, which strange enough is 72, and the voltage across the switch here is 0 times 6. So the wattage dissipated by our switch is 0. It won't get hot like that resistor did, but the bulb's on full brightness. When we open the switch, well, what happens now is that the voltage here is 0 and here is 0. So the voltage across our bulb is now 0. The bulb is off. The voltage here is 12 volts and the voltage here is 0 volts. But there's no circuit, so the current is 0. So now the wattage dissipated by our switch is 12 volts times 0 amps is 0. So when the switch is open or when the switch is closed, it doesn't matter which, whether the switch is passing 0 amps or 6 amps, the wattage dissipated by the switch is 0. And this is very important. Now let's consider what will happen if we switch this switch on and off rapidly. Okay, so what we have now as a switch, we can switch very quickly, okay, automatically, because our fingers are not fast enough. The piece of broccoli, sorry, the light bulb here. So here we have again the 12 volt supply, plus and minus. We're switching this switch on and off, on off, on off, on off. Okay, what's happening is the voltage here is switching between 0 and 12 and 0 and 12 and 0 and 12, yeah, at whatever speed we're switching the switch. Okay, let's say we're switching it as fast as we can with our fingers, 4 times a second, something like that. Okay, the voltage across the light bulb now is, well, 12 volts half the time and 0 volts the other half of the time, assuming that we're pressing the switch closed for the same amount of time as it's open. Okay, this is a square wave, going between 0 and 12. The duration of the wave, and this is one wave, from the rising point here to the falling and back to there, so that classes as one wave, and then it repeats. The rate at which it repeats is called the frequency. Okay, so we have the frequency. While we're on this, the height of the wave, how high it is, this is called the amplitude. Okay, and the proportion of the time it's switched on compared to the proportion of the time it's switched off is the pulse width. So when we talk about pulse width, that's what we mean. This one we can see is on for 50% of the time and off for 50% of the time, and then we get the next wave on for 50%, off for 50%, okay? And that ratio is actually called the duty cycle. And in the case of our switch, it's 50%. What happened to our circuit? Well, the light bulb will flash on and off at the same rate we're pressing the switch. And if we're managing to press that switch 4 or 5 times a second, it will flash, yeah. If we can even switch it at 10 times a second, and I doubt our finger will keep that up, at least not for very long, unless we use some mechanical vibrating device, okay, this will now flicker at a higher frequency. But if we can switch it on and off fast enough, we will no longer see the flicker, okay? Even if not allowing for the fact it takes the filament a little bit of time to warm up and cool down. Even if this was something like an LED, which will switch on and off basically instantly, our eyes cannot detect the flicker. It's something like, say, 50 or 100 times a second. A fly can, by the way. A fly has a much higher refresh rate on its eyes. That's why you can't swat one, by the way. It can see you coming far before you can actually get to it. But the human eye will not see that flicker, will not see the changing at that frequency. So we can put some sort of motor on here or some sort of electronic circuit, even better. We can switch this on and off very rapidly. The light bulb will now light up at half the brightness because it's on half the time and off the other half of the time. What's the power dissipated by the switch? Well, it's the same as this. It doesn't really matter how fast we switch that on and off. The switch is either closed, so there's 0 volts across it. The wattage is 0 volts times the 6 amps. 0 times 6 is 0. Or the voltage across it is 12. And at this point, it's open. There's no current. So now the wattage is 12 volts times 0 amps is also 0. So effectively, this very rapidly switching switch will dissipate no heat. In reality, there are some efficiency losses. It takes a finite amount of time to switch on and switch off, so there will be some heat, but the efficiency of this is going to be somewhere around 90%. So only 10% of the power is lost in the switching. 90% goes into the load, whereas this series resistor, the efficiency at best was 50%. So you can see this is a much better way to do it. Is this pulse width modulation? No. All we're doing is switching a square wave so it's on half the time and off half the time. The pulse width isn't changing, but what if we change it? So for example, what if we switch on for a very short amount of time and then off, then back on again for a very short amount of time and off. Like so. What if we do that? Well, what will happen is the bulb will go dim, because now, in this case, say the duty cycle is now 10%. The switch is only closed 10% of the time. Okay, so we get 10%. We'll effectively get 10% of the voltage across our bulb, 1.2 volts. Okay, and of course we can go the other way. Yeah, we can go the other way. So I'll try to keep it on the same graph if you like. So we now switch on for a very long time, switch off for a short time, back on for a long time, short time off, back on. Okay, try to keep level by a bit of paper, like that. The duty cycle now is, say, 90%. So now 90% of the voltage will appear across here, which is 10.8 volts. Okay. But the efficiency still stays at effectively 100% or close to it, because this switch is only ever open or closed. It's never half and half. That, by changing the width of the pulse, this is modulation. I told you it would become clear, yeah, what modulation is with an example. So what is pulse width modulation used for? Well, we can see that it is used to regulate or vary the amount of voltage and thereby current supplied to a load. Okay, and the load could be a lamp like I used, it could be LED or strips of LEDs, yeah, lots of LEDs. It could be a motor, it could be something purely electronic, a CPU, a GPU, anything that we want to supply with a certain voltage, or for that matter with a certain current. So PWM is mainly used in power supply applications. Things like your wall, your switch mode power supply, your power bank, your power pack, that sort of thing, okay? Switch mode power supply. That uses PWM to regulate the output voltage and or the output current. Things like DC to DC converters. These are circuits you find in just about any device. So most devices these days are digital. They actually run on a very low voltage or number of voltages. So RAM will need a voltage, the processor will need a voltage, or the logic circuitry will also need a different voltage. Yeah. So DC to DC converters, this takes a power supply coming in, say 12 volts, and it will generate things like the voltage to the RAM, the voltage to a CPU, the voltage to the interface, say to the HDMI, that sort of thing, okay? These are often called buck converters as well. And for that matter, we get boost converters that take an incoming voltage and give a higher voltage out rather than a lower voltage out. A commonly mentioned thing, VRM, voltage regulator module, found particularly on graphics cards and motherboards. That's also a form of DC to DC converter. So this is where we find PWM used, but there's another main application as well, and there will be no doubt other more esoteric ones, but the other one is class D amplifiers. This is a type of audio amplifier that basically uses pulse width modulation to carry the signal, the audio signal. So with a class D amplifier, you actually take your audio signal coming in and you sample it very rapidly and produce a pulse of a given width. The higher the voltage at that point, the wider the width. Okay. Now this will highlight something important I should have said before, but I didn't. But with pulse width modulation, the carrier, the square wave, the thing that's being modulated, will be a much higher frequency than the information you want to carry. So for example, with the class D amplifier, you may want to carry information which is basically the changing voltage of a sine wave, and you need to sample this sine wave at many points. Okay, the more points you sample it at, the more accurately you can carry the information by modulating the pulse width. So that's where PWM is generally found. Now, you may think that pulse width modulation is a digital process. Yeah, a digital process. But in actual fact, pulse width modulation has been around for a very long time. Much longer than we've had microcontrollers. For example, things like Arduino boards and various other embedded microcontrollers. PWM, in actual fact, has been around since commercially, at least in the 1960s, mid-60s. Became more popular into the late 70s, into the early 80s when we started to see a lot of it, and these days it is ubiquitous. But PWM is actually an analog process. Although you may see things like vacuum cleaners that claim to have a digital motor because they use PWM to control it or drive it at very high speed, It's not digital at all. PWM is not digital, okay? It is analog. So let's have a look now how to make a circuit, a very basic circuit that gives PWM. And then let's build that on a piece of breadboard and let's have a look to see how it works. Pulse width modulation is generally implemented with dedicated PWM ICs and microcontrollers. Obviously they can do this as well. But the basic principle is easy to implement just using generic ICs such as oscillator chips, 555, timer, op amps, those sort of things. So that's how we're going to do it. We're actually going to build a pulse width modulator, not using discrete transistors, though we could do that, but using basic building blocks, okay? So our pulse width modulator consists of two parts. We have an operational amplifier that is used as a comparator, okay? So with a comparator, we have two inputs. And normally speaking, one of these inputs, this can be inverting or non-inverting, by the way, whichever way you want to build the circuit, but the basic is that if we put a variable resistor here, this is your positive supply rail, let's say plus 9 volts, because that's what I'm going to use when I build it. This is 0 volts. If the voltage at this input is above the voltage on that input, so we'll put some voltage on here. In fact, let's just use a fixed pair of resistors, okay? 9 volts, 0 volts. If we adjust the potentiometer so the voltage here is above that one, even by an extremely small amount like microvolts, the output will go to 9 volts. Okay, and if the voltage here is below the voltage there, again, even by an extremely small amount, the output will go to 0 volts. So that is a comparator. It compares two voltages. How does that help us build a pulse width modulator? Well, we need one other part, and that is an oscillator. Okay, and we want a sawtooth. A sawtooth is a waveform that effectively goes up and then comes down instantly, goes up, comes down instantly, goes up, comes down instantly, and so on. That's a sawtooth. Okay, and what we do is we take our sawtooth and we connect it to our comparator. Okay, that's out. The other input we connect to whatever signal we want to modulate the oscillator with. Let's just picture what happens if we have a certain voltage on here. So what happens on the output? Well, this is ramping up and down. Let's say it's going between 0 volts and 6 volts. Okay, so while the voltage here is lower than the voltage there, the output will be low. Only when the voltage here is higher than the voltage there, it'll be high. So if we put, say, 3 volts on here, the sawtooth will ramp up, and during all the time it is below 3 volts, which we'll say is there, the output will be low. Okay? At the point at which it goes above, the sawtooth goes above the 3, the output will go high to 9 volts. Okay? And it will stay there until the sawtooth comes back down again, which means it will go back to 0 again. And the same thing will happen again. So at this point here, the waveform will go high, low. Yeah? And I'm sure you can see straight away, if we decrease the voltage here, then the sawtooth won't have to go so high. Maybe if we bring this down to 1 volt, the sawtooth only goes up to 1 before it switches. So the frequency stays the same, but the duty cycle changes. I'll draw it on this one, it's a bit easier. So the first example with 3 volts input, which we'll sort of put there, the waveform switch reaches this point, so we get a pulse like that, which was supposed to be 50%, but you know, this is hand drawn, yeah. When we reduce this voltage down, say to here, the output waveform now switches at that point, so as the sawtooth gets to here, it switches, and this stays on again till it drops. And again, just make sure I do this in the right place. At the point when it reaches the 3 volts, it switches again, like that. So that's how it works, yeah. I did get it right. Okay, there you go. So you can see that all we need is a sawtooth and an incoming signal, yeah. And we can build a pulse width modulator. The chip I used was an LM393. This is a dual comparator, but I'm only actually using 1/2 of it, one of the comparators. And the chip I've used for the oscillator is a 555, NE555. Very common chip. I found the circuit online for the NE555 sawtooth generator here, okay, sawtooth wave generator. So I borrowed that one, that's the one I've built, and the LM393, I've connected it just as I showed in that example on the paper. Okay guys, and I've built that circuit, we can see it here on breadboard. So this is the 555 timer chip. This one is an LM393 dual comparator, but I'm only using one comparator. And on the oscilloscope, we can see 2 traces. So the cyan one, this is the output from the 555, the sawtooth wave, and the yellow one, this is the output from the comparator LM393. And if I alter the frequency here, wait a second, change the frequency of the oscillator. Okay, I can make it slower. That's the maximum with the components I'm using, so that's a 100 nanofarad timing capacitor and a 470 ohm resistor. Okay, so that's giving me around 8 kilohertz. The other potentiometer here, this is adjusting the reference voltage on pin 3 of my comparator. So if I turn the reference voltage up, you see we can make the pulse width, that's the yellow trace that you see here, this yellow one. We can make that narrower, much lower duty cycle. And if you watch this LED, you'll see the LED is going off. Okay, it's dim. As I go the other way, the LED is getting brighter until we reach the maximum duty cycle there. Okay, that's about 50%, for example. So there's the pulse width modulator in operation using the 2 chips as I described on paper, and that works very well. Let's try, instead of using the reference voltage from the potentiometer, let's use a sine wave instead on this input, and let's see what happens. So I'm going to generate the sine wave with my signal generator, and this will be at a lower frequency. Okay, I have it running. I've actually set the sine wave down at 100 hertz. So once again, on the cyan, you can see the sawtooth wave at 8 kilohertz. And here we can see the pulse width modulation. You can see it's changing all the time. So if I just lock my scope, there you go. And you look along the trace, can you see that? That the actual width of the pulses, the yellow ones, is getting narrower, wider. Okay, let me see if I just get a longer sample than that for you guys. So I'll reduce the scale a little bit. So I think you can quite clearly see there on the yellow trace that the pulse width modulation is changing. I've now reduced the frequency of the incoming sine wave further, so it's now running at 1 Hz, 1 cycle per second. And you can see on the cyan trace, this is the sawtooth wave. I'm sorry, my scope is just losing synchronization occasionally, even though I try to set a trigger, but we won't worry too much about that. And the yellow one, you can see the pulse width modulation there running from effectively 0 to near 100% duty cycle. Okay, and if you look at the LED, you'll see it's flashing on and off. So the data, which is the changing voltage, is being sent to the LED via the carrier, the 8 kHz sawtooth. Okay, let's go down a little bit lower in frequency again. Okay, so now we're running at 0.1 Hz, so you can clearly see the pulse width modulation at that speed. I don't have quite the amplitude set, so it looks like the incoming sine wave is actually going below the voltage of the sawtooth. That's why it goes below 0 duty cycle, just there. Okay, but with a little bit of tweaking, we can make sure that it's stayed within range and it's not going quite to 100%. And once again, our LED is flashing on and off slowly. So I think I'd like to take this a bit further if you guys are interested on the next sponsored video from PCBWay. What I'd like to do is put together a little development board where we can effectively change the frequency of the 555, get it running at much higher frequency. We can try feeding in an audio signal, okay, and we'll drive something like a MOSFET from the comparator. We'll need some filters, that's just inductors and capacitors, and we can probably build a Class D audio amplifier and see how it works. It's not going to be anything of audiophile quality because this is something to play around with. For sure, we could just get some IC and do this, but I think building it from its constituent parts like this will help us to understand the circuit. And when it comes to repairing this sort of thing, understanding it is of very great importance. I did say originally, the title from this video, all you need to know about PWM to fix stuff. So what generally goes wrong with pulse width modulation? Well, normally speaking, what goes wrong is not the pulse width modulator, but the circuit, or rather device it is driving. So the output MOSFETs, the transistors, whatever is handling the high power, that's what tends to fail. And especially if you get, for example, a short circuit on the output of a power supply, it can damage the power supply. A short circuit on the output of an amplifier can damage the amplifier. So if you've got PWM based circuits that are giving no output or just blowing fuses when you plug it in and such like, the first place I would be looking at is the output devices, yeah? The pulse width modulator, the oscillator type thing, the controller, usually on its own right will not fail. Sometimes the circuits it requires to supply power to start up may fail, so it doesn't get any power to start off with, therefore it can't run. But all in all themselves, they're reliable. You can have faulty timing components, the capacitor, the resistor that sets the frequency, but again, that's not generally doing too much work and they usually don't fail. But if you do have a problem with a PWM chip, it's most likely being caused again by a failure in the output devices. So if you have a MOSFET driving some sort of load, that's what's doing the grunt, the hard work, the MOSFET goes short. If the MOSFET goes short from drain to source but not to the gate, your controller chip which is connected to the gate may be just fine. If the whole thing has gone short, it's possible that a lot of high voltage went straight into the pulse width modulator controller, usually an IC, and caused it to blow. So really that again brings us back to the output devices normally cause the problems in PWM circuits. Hope you enjoyed that. I'd love to hear from you guys in the comments below. we'll get on building a little bit more of this. So any topics you want to raise in the comments now, if we can't answer them in the comments, let's play around with them on the next installment. Okay, hope you enjoyed that, and I look forward to seeing you all soon on Learn Electronics Repair. Ciao for now, guys.